So the last step for implementing our backpropagation part is implementing the backpropagation for the convolution layer. And that's going to be the most tricky part, I would say, because we have to apply this equation that you see here, the convolution equation, but just backwards. And I just want to remind you also here on the process. So we have these different windows, and then we multiply those values, the weights in those windows in our convolution filter with the pixel values and sum them up. And that is pretty much the same process that we have in a neuron. So the idea is that we interpret the convolution filter as a neuron, and of course we also add the bias. So we multiply the weights with the input, which are the pixel values, sum it up, and add the bias, and this is the pixel value for the output image. So, and if we remember from the first part of this lecture, when we created the core of our dense layer and implemented the backpropagation, then we found that the changes in the weights, in the inputs, in the biases can be calculated by these three equations. So we needed the values. This is, again, the outer derivative coming from the layer which is below the current one, and then we multiply this with the inner derivative, which is in the case of the weights, the inputs, in the case of the inputs, the weights, and in the case of the bias, times 1. So therefore, let's go back again and just remember how a single neuron is applied to a data set in the forward part. So in the data set, we have the samples for each row and the weights for each column. So the columns are representing the different features or dimensions of the data points. So we must have as many weights as features. So therefore, if we apply a single neuron, then for every input, so for every data point, it multiplies the weights with the inputs and sum those values up, and also, of course, adds the bias. So therefore, for every data point, we'll have one value. So we'll get a vector. And now if we want to do the reverse, so let's say for the weights, so we want to calculate the weights, then we have to multiply the d values with the inputs. And of course, the d values must have the same shape as the outputs because they come back to the backward part. And we want to multiply this with the inputs. So the only way how to do this is this way. And then, of course, for every weight, we will have a dot product, the values times the vector that goes over all samples, but for one particular weight, so that we get a value for each weight. And of course, it makes sense, right? Because if we have only one neuron, let's say, like in this case, with 4 weights, then we should get a vector with length 4. So now let's do the same thing for the inputs. And of course, the inputs are the inputs for the next layer, which is above. Then they will be the d values. The only case when we do not need that is when we have the first layer, because that's where our images are, the inputs. And of course, we don't need the inputs. So we don't need to do this for the first convolution layer. However, since we have a class convolution layer, we will include this equation anyways. And we just don't use the data then for the first layer, for the first convolution layer. So again, the values is a vector, and now we multiply this with the weights, but we have only, let's say, 4 weights, and the only way how to get a matrix that has the same shape like the inputs is to multiply every weight with every d value, and that also makes sense. Because in the forward process, for every data point, we got the dot product with the weights. So we have to do the same process reverse. Well, and finally for the biases, it's just minus d values. So we have the d values. What is the d biases then? Well, if we have one neuron, like in this case, we just sum up all the d values and that gives me the d bias. So we just need to apply this to our convolution layer. So let's go to the backward part. And also here we can actually copy and paste a lot from the forward part. So of course we have the d values as an input. And we need the biases and the weights. And we need the stride and the padding. And of course we need the kernel shape and the kernel number. And also we need the padded image. So now it's the first layer where we have an actual derivative. Remember, the flattening layer was just rearranging the data, so there was no derivative. And the max pool layer did also not change the values. We just extracted the maximum from the corresponding windows, but the values were not changed. So the derivative was just multiplying it with the mask. So now we have an actual derivative, as discussed earlier, and now we need to apply these derivatives in the backward part. So we get the image, the padded image, and because we started with a padded image, and now we have to do the reverse process and unpad the image, so to say. So we have to cut off the edges which came from the padding. So then we know how large the inputs are because we know how large the padded image was. But now we have to be careful with the shapes because remember the incoming matrix has the number of channels as the third entry in the size and the shape. But then after it passes the filter with nk kernels, then this number will correspond to the number of kernels. So the incoming matrix, this quantity is the number of channels. The outgoing matrix, the output matrix, this is the number of kernels. So if we talk about the inputs, we want to have the same shape as we have from the input matrix. And that's the reason why this here is the number of channels, not the kernel number, which would have been the fourth index. And that's the reason why there's no S3. So that's not a typo, that's on purpose. Then also for the biases, we know how large the D bias is and also the D weights. That's also easy. And we also have to run our nested loops now in the coordinates of the D values. So that's what we did earlier already for the max pool layer, for example. And of course, the number of channels is S2, what we discussed a few seconds ago, and then we still have the number of images. So now we have all the variables, and now we want to just extract one padded image. Of course, it's the same for all k, right? Because that was the input image, where this quantity is the number of channels, and this quantity is the number of kernels. Okay, so now we just copy and paste the forward part. But of course, we have to be careful here. Now it's yd and xd because we're in the coordinates of the values. And then also we do the slicing. Then we have the current slice. Now we just apply the derivatives. So let's start with the weights. So the weights was the input times the d values. And the input, of course, was what we have in the current slice. And then we multiply this with the d inputs. And remember, every kernel was a neuron. So therefore, we have to add up all those products here throughout the different coordinates, x and y, because that would correspond the application of such a neuron to one particular image. But then, of course, the same filter applies for all the other images. But also for all images I. Then we need the inputs, and that is the product of the weights and the d-values. So also here, the weights refer to the particular kernel, and we have the inputs for all the different slices, so the weights times the d-values. And finally, we have to sum up for the biases, for the d-biases, and the sum goes over all coordinates, x and y, and kernel-wise over all images. All right, and then we have to depad the image, and then we have to save the inputs. And that's it. So that's the backpropagation part. And now let's implement the backpropagation part. So therefore, let me just move to the other screen. And now let's implement the backpropagation part. So we have quite a huge module, right? So we have a class that reads and scales the image. We have the max pool. I added also a min pool and average pool, so you can download this from my GitHub repository if you like, and you have it complete. We have the convolution layer, of course, then flat, dense layer, sigmoid, tangents, hyperbolicus, ReLU, and all the other things. And now we go to the convolution layer and add the backward part. And you see that's quite some code. So we have the convolution layer and we add the backward part. So let's say the backward. And we start with the values. Let's take some space here. Okay, so we need the biases. For determining the size of the biases. So we can actually do it like this already. So we can say the biases equals P0 and then we have the shape. And the same for the weights. Is NP0s and then the shape of the weights. Okay, what else do we know? Do we need? So we need the stride. And we also need the padding. And we also need the kernel shape and the number of kernels. So let's see whether we have that here. So we have the kernel shape and the number of kernels. So we can actually copy and paste this part here. And again, you don't have to do this explicitly. I just do this in order to keep the code a bit shorter. All right. So then we need the image padded and it was named self impad. So that's what we have here. Okay. And then we determine the shape of the padded image. Because we're going to need that for setting up the input values or the matrix for the inputs. So we have the image added shape, and now we can set up the inputs. So that's also, of course, NP0s. And now we have to be careful. So, of course, the first entry is the X values. Then the second entry is the Y values. Then the third entry is the number of channels because we want to have the shape of the incoming matrix, of the input matrix. And then S4 is the number of images. Right? Remember, image padded, if we just go to image padded, had the shape where we have the X coordinate, the Y coordinate, then we had the number of channels of the incoming matrix, and then the number of kernels and the number of images. So that's the reason why we leave this part out, because the output matrix should have the format number of so number of rows, number of columns, number of channels, and number of images. And then we determine XD, which is D values shape 0. Then we have YD, and the number of channels is then, of course, S2. And the number of images is S4. Okay, so now we have all the variables that we need. And I want to open another panel because I want to go to the forward part of the convolution layer, because then I can just copy and paste this part here. Okay, then let me just delete it and empty. Okay, so we have our image padded. And remember, the image padded is 1, 2, 3, 4, 5 dimensional, right? Because we had X, Y, number of channels, number of kernels, number of images. But now we have to take into account that the current image comes from the inputs. Sorry, from the value. So the current image comes from the D values. And that's the reason why we have one fewer dimension. And we can just say image padded equals this. Because now we can go into our loop here and can just remove one dimension. Because now we have to go over the different kernels, but also over different channels. But the incoming image had the number of channels, and we turned it into an image with the number of kernels. And now we have to do the reverse. So now the image that we get from the values has the number of kernels, and we have to sum up for the number of channels. And that's the reason why we made this extraction here. And of course, we have to do this in coordinates of the D values. Okay, so then we can also add these slices. So we can say sx equals slice. And then we have y start, x start and x end. And we're going to do this with y as well. Now again, keep in mind, in the forward process, the input image has number of channels, and then we add coordinates for the number of kernels, and then we sum up over the channels for each kernel. So the output image has here the number of kernels. And now we do the reverse process in the backward. So D values has the number of kernels, but we have to sum over the number of kernels for every channel, because the inputs must have the same shape as the input image in the forward part. Okay, so then we have the current slice. And what is our current slice? Well, it's the current image padded over slices, sx, sy, and c. We don't have an I here because we extracted it here. So now we can add the derivatives. So now we say we have the d weights, and remember the d weights. So the weights are the neurons. So for every kernel K, we have only one neuron, and this neuron has, of course, rows and columns. So that's the number of the weights then, rows times columns. But again, it's one neuron per kernel, so one neuron per kernel. So therefore, we have to sum up all the products from the current slice, which is the inner derivative, times the d values, x, y, k, and I. So we sum up over all coordinates x and y, and over all images, because we have one neuron per kernel, which goes through the entire image. So that's the reason why we sum up over X and Y. And also we apply to all the different images. That's why we have to sum up over I. And we do this for a specific kernel. It's actually lots of information that one particular kernel gets. Right? For example, it's just the size 4 times 4. It's 16 weights. But it gets the information from all the images and all the coordinates. Now we add the inputs. And the inputs, of course, for the slice as X, as Y. And then, of course, we have C and Y, as C and I. And then we have to get the influence from all the weights. And of course, these are the weights of the corresponding kernel. And then we multiply this with the d values again. And now we add the biases. So let me just check we need the weights. Let me just add this. Of course, we need the weights. So just the weights equals still weights. All right. So we have the weights and we have the d-values. Okay. And remember the biases was just the sum over, so we have only one neuron, and so one neuron per kernel, and it gets the information from X, Y, and all the images. So in order to get a d-bias, we have to sum over those variables, X, Y, and the images. And then we get the d-bias for every kernel. So therefore, we can write it in the loop for K. So where we just write down d-biases. Just make sure that's because it's a vector, which has only the length nk, but just make sure for the indices. So that's the 0th row and then all these different columns. And then we just sum up the contribution from the different images, because here we have the different images. Here we have the kernel, so we do this for all the different kernels. And what do we have to sum up? The d-values. But we have to sum up over all coordinates in the image for a specific kernel K and for a specific image I, but we still have to sum up over all the images. So therefore, let's first of all sum over the image coordinates. So that's really clear what we have to do. So first I sum over all rows. Then I have to sum over all columns. Which is then the new x is 0. Right? So after d-values, and the values have x, y, k, and I. So I have to sum over those coordinates. That's what I do here. and I have the values for a specific kernel, K. But of course, I have to do this for all the images because one neuron of a specific kernel K, of course, goes through all the images. And that's what I do with the plus equal here, because that goes over the index I. That's what you see here. So once I go through all Y and X, I just apply those sums. That's the reason why it's outside of this loop and also outside of this loop. Okay, and then we have everything from the inputs that we need, and we just need to unpad it. So then we just say the inputs equals the inputs, and then we just know the padding, of course. So we just go from padding to S0 minus padding. And because the padding was adding an edge in both sides, up and bottom, left and right. And then we do the same thing for the X, for the Y coordinate. And the rest of the image or the rest of the matrix stays as it is. So we have the padding, X and Y that we remove, and then we have all channels and all images. Yeah, and that's it. So now we just have to save it and just make sure that it works. We just save the biases. And we also save the d-weights. All right, so let me just expand the window a bit and let's go through the code once more. So we first of all load all the information that we need. And we also pre-allocate matrices. So we know that the incoming image has the number of channels as the third coordinate. And the values has the number of kernels as the third coordinate. Because that was the idea in the forward part. So the input image had a number of channels, then we performed convolution, and the output image has then the number of kernels as the third coordinate. So that's the reason why we know that the inputs must have this particular shape. So then we get the image padded, and remember the image padded had the X and Y coordinates of the images, the number of channels. We prepared it for the number of kernels and also then the number of images. So it has one more dimension. So we have to run this loop in coordinates of the padded image. And since we have one fewer dimension, because the resulting image must have the shape of the inputs. So X, Y, number of channels, and number of images. We can just extract one. It's completely arbitrary if we have a 0 or 1 or 2. So now we run our nested loops, but now in the coordinates of the D values. We just go through the windows with the heading, with the stride that we had, create the slices and then the current slices. And then we just follow the derivatives. So the D weights were the inputs times the values. And remember, every kernel has just one neuron. So therefore, we have to sum up over all the image coordinates and over all the images for one specific kernel. For the D inputs, we want to have a matrix that has the same shape as the input matrix. So therefore, the coordinates are the slices, channels, and images. And again, we have one neuron per kernel, and we multiply this with the D values. That was just the autoderivative. And the values goes over the image coordinates and the different images. So we sum up over the weights of the different kernels and the coordinates and the different kernels. And the biases, that was just the sum over all inputs, so to say, so the values per kernel. We also sum up over the images. That's what we do with the plus equal here, because this is the images here. All right, so that code should work. And therefore, let us go back to the PowerPoints. And let's remember what we did. So we added the backward part. And as I said, so this code should work. And we are now done with coding, with setting up our CNN. So that's actually the first milestone. So I would say congratulations. That's your first self-made CNN. But still, we have to test it. And that's the last chapter. So we want to test the CNN. So we want to really build the CNN with the forward part, the backward part, the optimization. I want to see whether it really learns. And then, of course, I want to say a few things about the training process and how to select the proper training sample.